All right, the final piece of the puzzle is proving the correctness of our algorithm. So our theorem for this is that Huffman's algorithm computes a binary tree that minimizes the average encoding length of all symbols, where the average encoding length is given by this equation, so L of t. So give it a tree, it'll tell you how many bits on average are you using to encode each symbol. Our strategy for proving correctness is going to involve induction, and it's going, oh, and just to remind you, our general template for induction is we have to talk about the base case, talk about our inductive hypothesis, our step, and then we can draw our conclusions. And we're also, since this is a greedy algorithm, going to throw in there an exchange argument, which usually makes our lives a little bit easier. So an inductive proof. We have to start with our base case. Well, our base case is a little more interesting here in that it's not just if we have one symbol, it's if we have one or two symbols. Well, if we have one or two symbols, well, if we have one symbol, you can represent that single symbol with 0, or you could represent it with 1 if you wanted to. If we have two symbols, you could represent it as 0 for A and 1 for B, or the other way around. The key point, though, is that they are going to end up with the same average encoding length. So you have two options here. They end up with the exact same average encoding length. So our base cases here are pretty trivial. There's no choices to make. If we have one symbol or just two symbols, we're done. Our inductive hypothesis. So we need to state something about what happens if we have fewer than n elements. So we'll say that Huffman's algorithm produces the optimal encoding when we have less than or equal to k symbols, where k is strictly less than n. Finally, we have our inductive step, where we have to say what are we actually doing in code and how does that relate to what we're trying to prove. For our inductive step, we're going to need sort of two main ideas. And for those ideas, I'm going to introduce two symbols. Let's say we have phi and pi. And let's say that that's the smallest and second smallest frequency symbols available respectively. So when would those two symbols be combined? Well, if they're the two small symbols, they have to be combined in the first iteration. Okay, so we have these two symbols. What we're going to use as our main ideas for our proof here is to say that Huffman's algorithm outputs the optimal tree in which phi and pi are siblings, or phi. Am I saying that wrong? Oh well. So basically we have a bunch of different possible trees, and there are a number of trees where these are siblings. They could be anywhere in the tree, so to speak. And we're just going to say Huffman's algorithm produces the optimal tree in which they are siblings. Okay, so what about all of the trees where phi and pi are not siblings? Well, that's our second part here. We'll say that the optimal tree is the one in which phi and pi are siblings. And for that, that's where we will do our exchange. Okay, so for part one, this part turns out to be fairly trivial because after we combine those two symbols into a single symbol, we've gone from having a total of n symbols to having n minus 1 symbol. And by our inductive hypothesis, we know that Huffman's algorithm outputs the optimal tree for that scenario. So after we combine two symbols, we know that we are left with the optimal tree. We know that it gets produced due to our inductive hypothesis. Okay, so out of all possible trees in which these two things are siblings, we know that we end up with the optimal such tree. Okay, so that's not very useful unless we can show that it's important that phi and pi are siblings. So that's part two. Part two, we have to say that the optimal tree is the one in which they are siblings, and we know we have the optimal one in which they are siblings. So let's consider the case where they're not siblings and see how that changes our argument. So let's say we have this tree. So to get to A, we have 0, 0, 1, so that would be the encoding for A. And I didn't put a symbol here because we're going to ignore it, and here because we're going to ignore it. And then to get to B, we have 0, 0, 1. Okay, so it takes 3 bits for both, 0. So it takes 3 bits for both of those symbols. How many symbols does it take for phi and pi? Well, they don't have to be right sort of next to each other here in the tree. We just know that they're not siblings. But we have, let's see, 1, 1 for pi, so that's 2 characters. And we have 1, 0, 1 for phi. Well, what happens when we do an exchange of find pi with the leaves that are furthest down in the tree that happen to be siblings? So A and B in this case. What happens when we exchange find pi with A and B? Well, we'll end up with this tree. And what does that do to the average encoding length? Well, our assumption here, again, was that phi and pi are the least frequent symbols. So when we push pi down and make it a sibling and move, let's say, either A or B, it doesn't matter. In this case, we're moving B up. What we have here is a net decrease in the average bit length. Or I can just use our L of t notation. So we have a net decrease in L of t, which means that we are better off with phi and pi as siblings if they're not siblings. There is one little extra bit to note here, and that's what if I was comparing, for example, what if pi was here and they were both at the bottom of the tree and not here? Or actually, rather, let me swap these two so that A was a sibling of pi and B was a sibling of phi. Okay, so it's true we don't get a net decrease there, but in that circumstance, we also don't have an increase. So our final bit here is that the average encoding length when you do this exchange goes down, or at the very worst, it stays the same if you end up with some ties in your total number of frequencies. So the net of it is a good or neutral change. Okay, so here's our summary. A prefix-free variable length binary code will have a smaller average encoding length than a fixed length code. That's assuming that you have varying amounts of frequencies per symbol. Well, Huffman codes can be visualized as a binary tree, and Huffman's algorithm works by greedily combining trees in the forest until you're left with just a single tree, and it does so very fast. Just longer than linear time, so big O of n log n. And then finally, we've proved correctness of our Huffman algorithm using an induction proof and an exchange argument.